Okay, good day, students. Welcome to GET 272 class. This will be the final lecture for the semester. So, like I promised you that I would make available online the 3 remaining topics for the semester. And if you recall, I mentioned that these topics are the first one, which was lecture 5. Okay, yes, lecture 5, imperfection in solids, and lecture 6 was mechanical properties of engineering materials, and the last that I promised is introduction to composite materials. So today I will be taking you through the lecture note 6, which is composite materials. So just like we have discussed some other class of material, their properties, will do same with composite materials in this particular lecture, and hopefully this will round up the class for the academic semester. So what we want to address in this particular class is to understand the concept of composites, the various classification of composites, the need for composite materials in engineering application, what are the mechanical properties of composite materials, and then we'll also try to understand some applications of engineering materials, this time around composites. So to start with, we need to first understand what the term composite material is. So generally, we have understood some unique class of materials, and these are metals, ceramics, polymers. So you see, these are basic engineering materials that have unique properties based on their structures, and we have understood what these class of materials are and how their structures determine their properties, and also how you can play around with their properties by manipulating their structures. Now you see there is a unique properties attached to these classes of materials that we have discussed. So for example, if you talk about metals, for instance, you are talking about materials that have ability to conduct electricity easily, materials with high ductility, relative strength, and all what have you. If you take polymer, for instance, you are talking about materials that are very, very ductile. You know, they have less strength when you compare to that of metals and ceramics. And then when you talked about ceramic material, you're looking at high strength materials that are not tough, that are brittle in nature. So you see, these are unique properties associated with this class of materials. Now you see, during the course of an engineering application of a material, you may desire properties that are outside the range of these unique properties that we have understand with respect to the other classes of materials that we have studied. So for instance, you may desire to have a combination of properties. So I give you a typical example of, say, ceramics. So you see, a ceramic material is a high strength material, but there is a downside to it, in the sense that being a high strength material means it is susceptible to being brittle. So now, if you desire an application of a material that require high strength without being brittle, say for instance you want it to be tough. So now you see, if you take a standard ceramic material, you cannot achieve toughness at the same time with the high strength. So you see, there is a problem there. So the higher the strength you achieve, the less toughness you will have, and the more ductile or tough you want a material to be, you will lose the strength properties. So you see, so sometimes when you desire a combination of property that is not achievable by the unique class of material. So what I mean is, there are certain desired properties that you cannot obtain from a metal alone. There are certain desired properties, combination of properties, that you cannot achieve by a polymer alone, or there are certain desired combination of properties that you cannot achieve from a ceramic alone. So you see, when you have this situation, it means that you are left with no choice than to resort to what is called a composite material. So the composite material now becomes a form of combination of two or more individual material. So the essence of this combination is that you want to have an intermediate property that will combine the properties of the combining materials to give you a unique combination of property. So when you talk about a composite material, you are trying to design a material, and the goal is that you desire a combination of property that is not achievable from the individual material. So take for instance, if you let me give you a typical example that will allow you to understand what I'm talking about. So if you have a short man, for instance, and he's going to take up a wife, he's definitely not going to go look for another short woman. So the implication is, if you take a short man and he marries a short woman, they're most likely going to have a short child. So if you desire a child that is not going to be as short, so the man will have to take up probably a tall woman. So the implication is that the resulting child may not be as short as the father, may not be as tall as the mother, but the child will take up combination of these two. So the child will just be relatively tall. So this is the kind of desired properties that you want to achieve from combination of materials in trying to form a composite material. So if you desire a property of, say, low density and high strength all at once in one material, it may be difficult for you to have a single material, say a metal or a polymer or a ceramic, that will give you this combination. So you need to combine materials with these unique properties together, and then the result of the combination is that you now have a composite that will be able to have a combined property resulting from this combination. So let's now scientifically understand what a composite is and have some examples of what a composite material. So technically, you define a composite material as a multi-phase material with chemically different phases that has a distinct interface. So what this means is that, first, you must understand that a composite material is a multi-phase material. So you have a combination of two different materials together. Now these materials are chemically different, so it means you can chemically differentiate between them, and then they don't in any way try to bond together chemically, so they are distinct. So this distinct means that there is an interface, there is a line that distinguishes between one of the material and the other. So you combine them in such a way that they are a phase that have distinct interface. So what it means is that you can visualize and see that these are two different materials that are combined together, and that combination does not involve any kind of chemical combination. So they are chemically different, they don't bond together chemically, the phases are distinct, and then you can see the multi-phase that is present in the material. So if you have this kind of combination, the resulting material is what we term a composite material. So what defines a composite materials by extension is that the resulting combination of material, the properties that result from the combination of material, will be superior to the properties of the individual components. So you must understand this. So what it means is that you are combining a material with high strength to a material that is ductile. So you have an intermediate property from these two. So the resulting property is better off than the properties of the individual material. If this is not the case, then the desire for a composite material is not necessary. So in the design of composite materials, so many advantages have been achieved. So the desire to design a composite materials can make you get a high strength material that is also lightweight. You can have eco-friendly materials, you can have environmentally resistant material, low-cost material, and there are so many examples which we are going to look at in the course of these lectures. So generally, in understanding what a composite material, basically based on origin of the material, there are two classifications of materials based on their origin. We have natural composite and we have a synthetic composite. So these are based on the origin of the material. So natural composite, as the name implies, are those ones that exist naturally in nature. So there are a lot of materials that are designed by nature that already has the composite properties. So typical example is wood. So the same wood that you know. So the wood is a strong and flexible cellulose fiber that is surrounded by lignin. So if you know a wood, you see the wood is made up of fibers in it, and then what is binding or holding the fibers together is that pigment, that liquid pigment that is referred to as lignin. So you have lignin and fiber combined together to form the wood. So you see, that's a combination of property. The fiber is one phase, the lignin is another phase. The combination gives you a wood that is strong and flexible. So another typical example is bone. So you see, the bone is strong and it's also soft. So what it means is that you have the collagen within an apatite, which is a material. So you see, the combination of these two will give you a composite material. So this is another typical example of a natural composite. So there are so many other examples of natural composite materials. Then for the synthetic composite, these ones are the ones that are synthesized, these ones that you produced, that you produce that is produced by man. Let me say it that way, I think it's easier. So typical example are glass fiber. So for instance, if you take glass, for instance, it's a very brittle material. Once it shatters on the ground, once it drops on the ground, or there's an impact and it's beyond what it can take, it will just shatter. So there are ways now that you can toughen a glass material by incorporating a fiber therein. So what it means is that even when the glass is struck by a load that is impacting more than what it can bear, you can see it will crack, but it will not shatter. So that reinforcement allows it to have better properties. So this is a typical example. Then concrete, for instance, concrete is another example of synthetic composite, where you have the aggregate and you have the cement. So the cement paste, the aggregate, that is the sharp sand, the gravel, all of them forms different phases in the composite material. There are so many other advanced composite like the carbon composite. So we're going to look at some of them in the course of this class. So talking about example of composite and how they find application. So I give you a typical example. Your bicycle fork is a typical example of a composite material. It has unique properties of high strength, weight reduced, design flexibility, and then the cost performance is extremely high. So usually the bicycle forks is made up of glass and carbon fiber, that allows you to have a different stiffness. So you see, if you look at modern day bicycle, especially those for sports, there are certain desired properties that they require those bicycles to have in order to enhance their effectiveness in the usage for sports. So some of these properties that is desired by these bicycle parts cannot be achieved with the unique classes of materials. So a combination of certain materials can allow you to have these properties that is aligned here for a bicycle fork. Another example is our pole vault. So if you know the sport pole vaulting, so you can see the pole vault, you can see the pole vault. So if you know this sport very well, you see this pole vault that is required for this sport needs to have certain unique property for this to be achieved. So the implication is the athlete is running with the vault, is going to struck it on the ground, and is expecting that this pole vault will bend in this manner, and he will be able to throw the athlete above a certain barrier. So you can see that if you decide to use the unique class of material, say a metal or a ceramic, there are so many issues that this will bring. If you take a metal, for instance, how do you expect a metal or a ceramic material to be able to bend in this form and then allow the athlete to be able to be thrown to the other end of the barrier? You see, certainly this is not possible. So that is that. If you also want to use a polymeric, with a polymeric material, for instance, you can have this bending, but you may not have control over the manner in which the athlete will be thrown to the other way, or probably it can bend and just collapse. So the implication is that for you to achieve a material that will give you this desired usage means that certain properties need to be achieved by the material. So you need properties like lightweight, because of course the athlete will carry it and run through a distance. The buckling resistance, so you should be able to resist buckling. It should be strong. It should have minimal twisting capacity. You should be able to control the twist. Then the density should be low. The stiffness should be a desired one, and it should have a good yield strength. So all of these properties that we want to achieve cannot be achieved by either a metal, a pure metal, or a polymer material, or a ceramic. You cannot achieve. So you need a combination of properties. So if you take a typical pole vault, this is what you have. So you have this structure in a typical pole vault. So you see it is made in layers. So you have the outer layer that is a carbon fiber with epoxy. So you see this is the combination. This is a unique composite material, carbon fibers in epoxy. If you look at the middle layer, you have glass fiber web, same in epoxy. So you still have the same glass fiber, but the design now, the architecture for the glass fiber is in form of a web, and you still have an epoxy. And then if you look at the inner part, glass fiber rings, inside. So you see all of this is a composite material. This is another composite. So you have a combination of different composite design to have this particular structure. So this is the implication. If you want to design material with some unique properties that are not achievable from a unique class of material, then you need to do a combination of materials. Now, another very important engineering application where composite have find useful application is the aeronautic industry. So if you look at the modern day aeroplane, the modern day aircraft is supposed to be lightweight in order to reduce fuel consumption and also to increase speed. So if you want to build the aircraft, you don't want to use materials that will increase the weight of the aircraft. You don't want to use materials that will not give certain desired properties. So in the aeronautic industry, composite materials have found great application in the design of the airplanes, the airplanes. So if this is a typical example of this is a typical illustration, sorry, of an airplane, a Boeing 757-200 aircraft. So if you look at it very well, you see most parts are made up of composite materials. So take for instance, if you look at the landing wings, for instance, it's made up of Kevlar and fiberglass. So you see this is a combination of material that is termed a composite material. If you look at, say for instance, the wings to the body fairing, this is made up of graphite, Kevlar, and fiberglass. So if you look at it so much, you see that most parts of the aircraft are made up of composite material. So if you look at so many parts of it, if you go through, you will see that they are all made up of composite. So the reason is very simple. With a composite material, you can achieve some unique properties that you can ordinarily not achieve with a unique class of material. So let's now understand what a composite material. Of course, there are so many examples of composite material. You have composite materials application in aeronautic industry. You have it applied in mechanical industries. You have it applied in building industries. You have it applied in automobile industry. So many examples. So if you take our modern cars, for instance, most of the parts of our modern car are made up of composite material. So the dashboard, the bumpers, so the body of the car, they are all made up of composite material. So those things you see on the car, the modern day car that you think is plastics or is polymer, it's not a pure plastics or a unique polymer. It's some designed polymer that is reinforced, or it's either reinforced plastics or some reinforced material, polymeric material. So you see, most of the essence is that if you build the dashboard of a car, for instance, with a polymer, the result you get is different when you build with a metal. So with a metal, it makes the car heavy. If the car is heavy, it means it will increase fuel consumption. It will also lower the speed of the car. So, but with a if you desire a lightweight material, then and you want to retain certain properties in terms of certain mechanical property, then the best way to go is to look at the design of composite material. So in understanding composite material, you must understand what makes up a composite material. So in understanding what a composite material means, generally, since we are talking about combination of materials in the design of the composite, then what you have is that there must be a matrix and a reinforcing face. So the faces that we say they are distinct, one of them is going to be the matrix face, and the other will be the reinforcing face. And this is important because these faces will have different roles to play in the eventual property of the composite material. So in the matrix phase, it is expected that the matrix is soft, it is more flexible, it is the continuous parts in the composite material. So the continuous part is what you call the matrix phase in the composite, and what it does is that this matrix phase is the one that will absorb whatever stress, whatever load you have imposed on it, and then it will transfer that stress to the other part. So you see, it's a win-win thing. So you have the reinforced, the matrix taking up the load and then transferring the load to the other phase, which is going to be the reinforcement phase or the dispersed phase. So what the matrix phase also does, it is protect the other phase, which is the dispersed phase. And then the second phase, which is the dispersed phase, is what you call the reinforcement phase. So this reinforcement phase too can come in different types, but generally it is called the dispersed phase. So what you expect of the dispersed phase is that it should be stiff, it should have high strength. It can be in form of particles, it can be in form of fibers, and so many others. So the general expectation from the dispersed phase is that you should be able to enhance the property of the matrix phase. So you see, what this means is that the matrix is the flexible and continuous part that transfers load or stress to the dispersed phase, and then it also protects the dispersed phase from the environment. And the dispersed phase, which is the reinforcement, which can come in form of a particle or a fiber, is one that is expected to enhance the property of the matrix. So by this, you now have a unique combination of properties to form a desired property based on the materials that are combined together to form the composite material. So if you look at this slide, you have an example here of a composite material. So you have fibers here that are in a matrix. So this is a typical example of a sketch rather of a composite material. This diagram here is that of a reinforced rubber. So a carbon black particle in synthetic rubber. So this is a carbon black particle in synthetic rubber. So this is a typical composite material. So if you just have an ordinary rubber, it will just exhibit the properties of a polymeric material with very low strength. So but when you reinforce with a carbon black particle, it allows you to stiffen it, it allows you to increase strength. So this is another example of a fiber reinforced composite. So here you have a fiber in a matrix. So you have this. So this is a particle reinforced composite, and this is a fiber reinforced composite. So the particle here is the dispersed phase or the reinforcement, while the rubber is the matrix. In this case, the fiber here is the dispersed phase or the reinforcement, and whatever you have used as the matrix here, as whatever material that is constituting the other phase, becomes the matrix phase. So generally, based on the design of the composite material, this particular slide defines the classification of a composite material. So generally, a composite material can be classified as either particle reinforced, fiber reinforced, or a structural material, a structural composite. So when you have this dispersed phase in form of a particle, then you have a particle reinforced material composite. If you have the reinforced phase in form of a fiber, you have a fiber reinforced composite. And if you have a structural arrangement, maybe in terms of laminate or a sandwich structure, you have a structural composite. So in terms of the particle reinforced composite, if the particles are large, you have a large particle reinforced composite, and if the particles are very small, you have a dispersion strengthening. So this is the kind of composite you have when you just disperse particle within a material to strengthen the material. Then for fiber reinforced material, this will be defined by whether the fibers are continuous or are discontinuous. If the fibers are continuous, it means that they are long fibers and they are aligned, they are straight, they are aligned, and they are continuous, they are not broken. So what it means is from one end to the other end of the material, the fiber is continuous. But for discontinuous fibers, it means you have chopped the fibers. So you have short fibers within the matrix. When you have short fibers within the matrix, you have a discontinuous fiber reinforced composite. Now, when these fibers are short, then there is possibility that they could be short and aligned, meaning that they are arranged in a particular order and they follow a particular orientation in the arrangement of the fiber within the matrix. So if you have that situation, you have an aligned discontinuous fiber reinforced composite. Now, in the other case is that those chopped fibers can be randomly oriented such that they are not aligned in a particular orientation. So that situation will give rise to a randomly oriented fiber reinforced composite. So in that case, you have another type, which is a randomly oriented discontinuous fiber reinforced composite. And the third one, which is the structure can come in form of laminate, and it can come in form of sandwich panels. So for laminate, what it means is that you are placing the composite, the materials that forms the composite are placed side by side each other. So by laminate, it means, say for instance, you have a composite material that is made up of material A, material B. So if you now have a structural composite such that you are placing A beside B, and then you continue with that alternation. So A, B, A, B, A, B, A, B. So you form a laminate. But for sandwich panel, it means in this case you have one of the material being sandwiched by the other. So for a sandwich panel, it means, say for instance, you have material A sandwiched by B, so you have B, A, B, just B, A, B. So you see that two materials, B, A in the middle, and then B. So you have put A in the middle between B and B. So you have a sandwich panel. But for laminate, you have A, B, A, B, A, B, A, B. So that is what you have in this case. So this is the classification of composite material based on their design. Okay, so now if you form a composite material, there are certain factors that defines or that affects the property of the composite material that you have designed. And those characteristics of the composite will be dependent on certain unique factors that you put into consideration during the course of the design of your engineering composite material. These factors are the properties of the matrix material, the properties of the reinforcing material, the ratio of the matrix to the reinforcing material, the bonding or the adhesion between the matrix and the reinforcement, and the mode of fabrication. So let me take the first one, the properties of the matrix material. So what this means is that the resulting property of the composite material is dependent on the property of the matrix material. So what this means is, if the matrix material is a high strength material, you should expect some level of high strength in the resulting composite. If the matrix material is a ductile material, you should expect some relative ductility in the composite material. Same way with the second one, which is the reinforcing material, the reinforcement material. Whatever the property of the reinforcement material is, you should expect a share of that property in the resulting composite material. So you see, these first two are very, very important in determining what the property of the matrix. So if you desire a property for a composite, you must make sure that that desired property can be achieved relatively from any of these two, either less or in excess. So what you need is, in order for you to determine the property of the composite material, the property of the two materials or that you are combining together to form the composite must be available in one of the combination of the materials that you are combining. So this is very, very important here. So these two will determine what the property of the composite will be. So the third one is the ratio of the matrix to the reinforcement. So now that we have understood that the property of the matrix and reinforcement are important in determining what the property of the composite will be, another very important factor is the ratio of their mix. So what it means is that usually in composite design, we make use of volume ratio. We make use of volume ratio. So the volume ratio for the combination is 1. So out of 1, so what it means is that you can have 1 simply means 100%. So 100% is the combined material. So for a volume ratio 1, so you must have a certain ratio for the matrix, a certain ratio for the reinforcement. So this ratio will have different properties on the will generate different property for the composite. So take an example. If you have a fiber reinforced composite with the fiber taking 0.1, volume ratio of 0.1, that is 10% of the combination. So it means the matrix is taking 0.9. The property of that composite will change if you increase the fiber to 0.2 volume fraction, meaning that you now have a matrix volume ratio of 0.8. So this will totally change the property of the composite material. So this will also change if you increase the volume ratio of the reinforcement to 3. So as you are increasing the volume ratio of the reinforcement, you are reducing the volume ratio of the matrix. So as you play around this ratio, you will observe that there will definitely be a change in the property. Whichever property you want to measure, there will be a change. So you can see how effective this particular factor is in understanding the property of the composite material. So usually in the design of a composite material, you want to have an optimum combination of the two materials. So take for instance, if you want to design a fiber reinforced composite. So what it means is that there is a particular combination of the two materials that will give you the optimum property. So what you need to do now is you need to play with the combination until you achieve this optimum property. So say for instance, you have a ceramic material, you want to toughen it with a fiber reinforcement, for instance. So what it means is you have to begin to you cannot just decide that, okay, I will put in a volume ratio of maybe 0.2 fiber in 0.8 volume fraction of the matrix, and then you stay there. So if you do that, you are not sure if you have attained the optimum property. So what you need to do is you need to play around with this volume ratio, and for each condition that you take, you measure what the property will be until you now know which of the combination will give you the more optimum property. Now another factor that can affect the property of the composite is the interaction, the property of the interaction between the matrix and the reinforcing material. So the bonding that exists between them will also determine what the property will be. So what it means is that if the bonding is weak between the interface, then of course you know that when you apply load, the material can begin to fail from that weak interface. And if the interface is if the bonding at the interface is very, very strong, so it means that you can expect that the property of the material will be better off. Then lastly is the mode of fabrication. The mode of fabrication will also affect what the property of the material is. The mode of fabrication here will mean that how do you arrange the faces, how do you put the faces together. So what it means is if you have a fiber reinforced composite, for instance, the property you will get when the fibers are aligned is different from when the fibers are not aligned. If you have a continuous fiber in the matrix, the resulting property will be different from when the fibers are short. Now, even when you have for a short fiber, if the fibers are short and aligned, the result is different from when the fibers are short and randomly oriented. So even when you have a randomly oriented short fiber, the result is different if they are randomly oriented in 2D or they are randomly oriented in 3D. So all of this, which is the mode of fabrication, we have direct impact on what the property of the composite material will be. So you can also classify a composite material based on the matrix that makes up the composite material. So this is very simple. If the matrix in a composite is metal, then that's a metal matrix composite. If the matrix is a ceramic material, you have a ceramic matrix composite. And if the matrix is a polymer material, you have a polymer matrix composite. So what are the unique benefits of either a ceramic or a polymer or metal matrix composite? So when you make a composite out of a ceramic matrix composite, basically what you want to achieve is to increase toughness. This is simple because the only problem you will have with a ceramic material is that it is less tough, simply because the strength is very high. So when you try to make a composite material out of a ceramic matrix, what you are generally trying to achieve is to increase toughness. So for a polymer matrix composite, what you want to achieve is to increase the stiffness with respect to the density of the material. So you know generally that the polymer material has a very low elastic modulus, which is E per cubic meter per density. So what you want to increase generally here is the stiffness of the material. So when you try to make a polymer out of a when you try to make a composite out of a polymeric material rather, what you want to increase is the toughness. And then for a metal matrix composite, what you want to achieve is to increase creep resistance. So the resistance to failure at high temperature, because the metallic materials at high temperature are susceptible to failure. So when you make a composite out of a metal matrix, so generally what you want to increase is the creep resistance of the material. So this is a pictorial evidence of classification of composite based on reinforcement. So you see that this is about the third classification we are looking at. We have looked at classification based on the origin, which is natural or synthetic. We have looked at classification based on the matrix material, which is metal matrix composite, polymer matrix composite, and ceramic matrix composite. So this is the third one, which is based on reinforcement. So based on reinforcement, you can have particle reinforced composite, fiber reinforced composite, you can have structural. For particles, you can have large particles as you have here, when the particle diameter is above 100 nanometer, and you can have dispersion strengthening when you have very tiny particle distribution within the matrix. For continuous fiber, so you have long fiber reinforcement. For discontinuous fiber, you have short fiber reinforcement. So under discontinuous, you can have aligned short fibers and you can have randomly oriented fibers. And then for structural composite, you can have laminate or sandwich. So for laminate, you have this, you just have the panels repeating themselves to have this, or you can have a sandwich structure as you have here. So you have one face in between and you have the other face. You have this face in between sandwiched by the other face in between. Okay. So let's now try to understand what a particle reinforced composite is by giving examples. So typical example of a particle reinforced composite is ferrite steel. So you have the steel is such that you have a ductile matrix, which is a ferrite metal, ferrite ion, and then the particles in there are cementite, that is iron carbide. So you see the ferrite ion is ductile, while the cementite is brittle. So if you combine these two, you have a spheroidite steel that has a unique property that is a combination of this ductility and this high strength that you have with cementite. Another example is cemented carbide. So cemented carbide is a combination of tungsten carbide and cobalt. So your cobalt is ductile, while your tungsten carbide is very hard and brittle. So this is a particle within a cobalt matrix, so you form a cemented carbide. Also very unique material that finds application in many engineering. So we have automobile tires, the tires that you know in our in our vehicle. So you see that tire is made up of a matrix that is rubber, that's polymer, that is reinforced with carbon. So that is why you see that ordinarily the tire will not be stiff. So it is the presence of the carbon particles that has increased the stiffness that you have. So that's a typical example of a particle reinforced polymer. Now if you have a particle reinforced polymer, what is the relationship between the property of the composite with respect to the properties of the materials that makes up the composite. So if you take a particle reinforced polymer, there is a rule of law mixture that defines for us what the resulting property of the composite will be with respect to the property of the constituent material. So here we are going to look at the elastic modulus of the composite. So there are two approaches to that. So what it means is that before you design a composite material, you can estimate what the property will be from the property of the individual material. Remember, in understanding what the property of a composite material is, I told you that you must first you must know that the property of the composite is determined by the property of the matrix, the property of the reinforcing material, the combined ratio, the combination ratio. So if you understand these three, it is sufficient for you to estimate what the property of the composite will be. So for a particle reinforced composite, you have a upper and a lower bound. Now this upper and a lower bounds, what it explains is that between these two bands, you can predict what the property of the composite will be. So the upper bound is defined by EC is equal to VM EM plus VP EP. EC is the modulus of the composite that you want to design. VM is the volume fraction of the matrix. EM is the modulus of the matrix. VP is the volume fraction of the particle, and EP is the modulus of the particle. So what it means is that for a particular, so if you take a volume fraction of 0.2, if you take a matrix with a volume fraction of 0.8, automatically you are going to have the particle having a volume fraction of 0.2. Remember, I told you that the total volume fraction will be equal to 1 since it's a fraction. So the total will be equal to 1. So a fraction of 1 is taken by 1 and the remaining is taken by the other. So this is going to be the EM is the modulus of the matrix, and EP is the modulus of the particle. So if you combine all this, if you do this simple mathematics, it will predict what the upper modulus will be. And then you can have the lower modulus for the same combination, for the same volume fraction. This is the equation that defines what the lower modulus will be. So what it means is 1 over EC is equal to VM over EM plus VP over EP. So what it means is if you want to produce a composite material with a particular combination, so what it means is you can know what the highest modulus and the lowest modulus will be. The highest modulus will be determined by the upper limit, the lower modulus will be the lower limit. So you now have a range of what your composite property will be. So what it means is if you now practically decide to fabricate the composite and carry out the test, the result you get will be within that range that you get from the upper and the lower limit. So this equation is what is called the rule of mixture, and this rule of mixture is applicable for particle reinforced composite. It is also applicable for the fiber reinforced composite. We will be coming there later. So this is it, and it's very, very simple. So this is also applicable to other properties, not only elastic modulus. So if you want to also measure the properties of a composite material from other properties, like you want to measure other properties like electrical conductivity, other properties like thermal conductivity, so you can do that. All you need to do is replace this elastic modulus by this property. So say for instance, if it is electrical conductivity that you want to measure, so instead of EC, it will be the electrical conductivity. Instead of it will be electrical conductivity of the composite. Instead of this EM, it will be electrical conductivity of the matrix. Instead of EP, it will be electrical conductivity of the particle. Same thing if it is thermal conductivity K. All you need to do is replace E by K, and then you still use the same equation. So this equation is enough for you to estimate what the composite property will be once you know what the combining ratio is. That is the volume fraction of the matrix, the volume fraction of the reinforcement, and you know the property of the matrix, you know the property of the reinforcement. So if you once you know this, then it means you are good to go. You can estimate what the composite property will be. So I urge you to go and look at the textbook Callister. You see some examples there that has applied this equation to determining what the volume fraction, what the property of the composite will be in the lower and the upper limit using these two equations. Okay, so I think this is halfway into the class. I will stop here as part 1 of lecture 7. So I will continue. I'll continue from the next slide in part 2 of the lecture on composite material. So I don't want to make it too long. So this is 45 minutes already. So I will continue the other slides for this particular lecture in the part 2 of the lecture. Thank you very much for listening.